Welcome to ring theory. Today we are going to explore one of the most beautiful and powerful concepts in abstract algebra, the isomorphism theorems for rings. Imagine you have a massive, chaotic warehouse full of different items and you want to organize it perfectly. These theorems act like a magical sorting machine that helps us take complex, infinite mathematical structures and shrink them down into manageable, perfect copies. By the end of this video, you will understand exactly how to collapse mathematical junk to zero and reveal the hidden identical structures underneath. Let us start by understanding why these theorems exist. Think of a massive warehouse. If you group everything based on what ends up in the trash bin, you create a simplified version of that warehouse. The isomorphism theorems are mathematical rules that prove this simplified warehouse is structurally identical to the final neatly sorted output of the machine. They allow us to take complex, infinite mathematical structures and shrink them down into manageable, perfect copies by collapsing the junk to zero. In algebra, these theorems act as the ultimate shortcut for proving that two seemingly different systems are actually the exact same thing in disguise. Now that we understand the goal, let us look at the first isomorphism theorem, which is the fundamental bridge between functions and ring structures. To understand it, we must define a few terms. A ring is a mathematical set equipped with addition and multiplication. A homomorphism is a function between two rings that perfectly preserves how those operations work. The kernel is the specific set of elements in the first ring that the function crushes down to zero. This kernel acts like a mathematical black hole, making it an ideal. Finally, a factor ring is a new ring made by grouping elements together using that ideal. This brings us to the mathematical formulation. We start with a homomorphism, denoted by the Greek letter phi, mapping elements from our starting ring R to our destination ring S. This function is our sorting machine. As it operates, it maps some elements to the zero element of S. We call this set of elements the kernel, denoted by K. The formula mathematically defines the kernel as the set of all elements R inside the ring R that the function maps exactly to zero in the ring S. Because the function preserves ring structure, this kernel is guaranteed to be an ideal of R. Now we can state the first isomorphism theorem itself. The formula shows R divided by K is isomorphic to the image of R under phi. Here, R over K represents the factor ring, which is the original ring grouped by the kernel. The equal sign with a wave over it means is isomorphic to, which translates to is structurally identical to. Finally, the image of R is the actual set of outputs produced by the function inside S. The formula tells us that collapsing the kernel to zero creates a perfect copy of the function's output. Before we move on to the proof, let us see this with a concrete example, using numbers you are familiar with. We will look at the standard integers and map them to a clock math system, specifically the integers modulo 4. Our function phi will take any normal integer and map it to its remainder when divided by 4. For example, if we input 5, the output is 1, because 5 divided by 4 leaves a remainder of 1. To use the theorem, we must find the kernel. We need to ask which integers give a remainder of 0 when divided by 4. Continuing with our example, we identify the kernel. The kernel K is the set of all multiples of 4, which we write mathematically as 4z. Every number in this set is crushed to 0 by our function. Now we can apply the first isomorphism theorem directly. By dividing the infinite set of integers by the ideal of multiples of 4, we create a factor ring. The theorem guarantees that this new factor ring is structurally identical to the image of our function, which is Z4. We have successfully turned an infinite ring into a finite ring of 4 elements by collapsing the multiples of 4 to 0. So we have seen the formula in action. This brings us to the proof. To prove that two rings are isomorphic, we must create a new function between them and prove it is a perfect one-to-one matching that preserves addition and multiplication. We define a new function, psi. Its input is a group from the factor ring, written as r plus k. Its output is simply the original function's output for the element r. Before we can use this function, we must prove it is well-defined. This means if we pick a different representative for the same group, the function must still give the exact same output. Let us prove this well-definedness. Suppose we have two elements, A and B, that represent the exact same group in the factor ring. By the definition of factor rings, this means their difference, A minus B, must live inside the kernel K. Because it lives in the kernel, we know exactly what the original function phi will do to it. Since A minus B is in the kernel, applying the function phi to it results in 0. Because phi is a homomorphism, it preserves subtraction, allowing us to split this equation apart in the next step. Finishing our well-definedness check, splitting the function shows that phi of A minus phi of B equals 0. Moving phi of B to the other side proves that phi of A and phi of B are exactly the same. This proves our new function psi is well-defined. No matter which item you pick from the group, the output is identical. The rest of the proof, showing it preserves addition and multiplication and is a one-to-one mapping, follows directly from the properties of phi. This gives us our final proven result. To make this completely clear, let us look at a visual summary of the proof we just walked through. On the screen, you see the main ring R mapping to the destination ring S via the function phi. Inside R is the kernel K, which maps directly to 0 in S. Instead of traveling directly from R to S, you can take a detour. You can project down to the factor ring R over K, represented by the bottom circle. From there, the dashed line representing our new function psi provides a perfect one-to-one bridge to the image inside S. This triangle of arrows commutes, meaning both paths give the same result. Now that we have mastered the first theorem, let us move to the second isomorphism theorem, often called the diamond theorem because of how its sets are drawn in diagrams. Think of it like merging two different departments in a company. You have a main company, which is the ring, a specific department, which is a subring, and a company-wide rulebook, which is an ideal. The theorem tells us how the department interacts with the rulebook. A subring is simply a smaller ring that lives entirely inside a larger ring. The theorem states that if you add the subring and the ideal together and then factor out the ideal, it is exactly the same as taking just the subring and factoring out the overlap between the two. Let us look at the mathematical formula for this interaction. In this formula, S is the subring and I is the ideal. The expression S plus I represents the combination of elements from both sets. The left side of the equation means we take the combined set and collapse the ideal I to 0. The right side means we take only the subring S and collapse the intersection or the overlap to 0. The theorem proves these two resulting structures are identical. If you increase the size of the subring, the overlap with the ideal also changes, but the structural balance is always perfectly maintained. Let us see the second isomorphism theorem in action using the integers. We will set our main ring to be all integers. We will choose our subring S to be the even numbers, or multiples of 2, and our ideal I to be the multiples of 3. We want to see what happens when these two systems interact. First, we need to figure out what happens when we add these two sets together to form S plus I. Because 2 and 3 share no common factors, adding multiples of 2 and multiples of 3 allows us to generate every single integer. Therefore, the combined set S plus I is just the entire ring of integers Z. Continuing with our example, we now have the combined set. Next, we need to find their intersection. S intersect I. The intersection represents numbers that are in both sets simultaneously. A number that is a multiple of 2 and also a multiple of 3 must be a multiple of 6. Therefore, the overlap is the set of multiples of 6, written as 6z. We now have all the pieces we need. The combined set is all integers, the subring is the even integers, the ideal is the multiples of 3, and their overlap is the multiples of 6. Now we plug these pieces into the second isomorphism theorem to get our final answer. Substituting our findings into the theorem's formula gives this beautiful result. The left side is the integers modulo 3, which has exactly 3 elements, 0, 1, and 2. The right side is the even integers grouped by multiples of 6, which also has exactly 3 elements, 0, 2, and 4. The theorem proves that the way addition and multiplication work in these two distinct systems is structurally identical. Physically, this means a clock with 3 hours behaves exactly like a clock with even numbers up to 6. Moving forward, we arrive at the third isomorphism theorem. This one is the easiest to remember because it looks exactly like cancelling fractions in basic arithmetic. Imagine you have a fraction like 24 halves divided by 4 halves. The 2's cancel out, leaving 24 fourths. This theorem does the exact same thing, but for rings and ideals instead of numbers. It tells us how to simplify a factor ring that is being divided by another factor ring. It is a powerful tool for reducing nested, complex structures into a single simple factor ring. Let us look at the formula that makes this cancellation possible. In this formula, R is the main ring, I is a small ideal, and J is a larger ideal that completely contains I. The expression R over I is a factor ring, and J over I is an ideal inside that factor ring. The left side of the equation shows a fraction of fractions. The theorem proves that you can cancel out the small ideal I from the top and bottom, resulting in the much simpler factoring R over J on the right side. If the ideal J grows larger, the resulting factoring becomes smaller, just like increasing the denominator of a fraction. You might be wondering, why do we spend so much time learning how to collapse rings into factor rings? In the real world, computers have limited memory and cannot process infinite sets like the integers. The isomorphism theorems allow computer scientists and cryptographers to take infinite mathematical spaces and map them down to finite, secure systems. For example, modern encryption algorithms like RSA rely entirely on modular arithmetic, which is just a real-world application of factor rings. By proving that a complex system is isomorphic to a simpler one, engineers can perform calculations on the simple system and know with absolute certainty that the results apply to the complex system. We have covered a lot of ground today, so let us summarize the key takeaways. The isomorphism theorems provide the fundamental rules for simplifying algebraic structures. The first theorem shows that dividing a ring by a function's kernel creates a perfect copy of the function's output. The second theorem explains how subrings and ideals interact when combined and intersected. Finally, the third theorem acts like fraction cancellation, allowing us to simplify nested factor rings. Together, they are the most powerful tools in ring theory for proving that two different mathematical systems are structurally identical. Great job following along. You now understand the core of ring isomorphisms.